So, now let us see what Taylor did. So, we are at the last lecture of the course, and our aim is to tell you about the Taylor's theorem, give certain examples and finish off. After that you can take up the study further. I would rather suggest that you really look at good text rather than a text which I am trying to tell you, rather than arbitrarily looking at internet resources, and many of the times those resources tell you things which can be wrong. So, now I write down a polynomial function. Polynomial is something which you know, which is very simple, which is taught at a very basic level. So, it is a truncated power series actually. So, this polynomial is called a nth degree polynomial for xn. If an is not equal to 0, then it is called a polynomial of degree n. Now, suppose I know the function value at a, f a is known to me. Or f x is known to me, some x, does not matter. Then what is f of a plus h? That is the question. So, if I know what is a, then what is f of a plus h? So, when I write x is a plus h, my a is fixed. So, what I do, I write a0 plus a1 a plus h plus a2 and so on up to you can say, okay, I can do binomial expressions and I can do something with it. Then I will be able to write down the coefficients, the new ones. Taylor found a very simple way to do that. So, what would happen if I do a0, then a1 plus a1 into a plus a1 into h. So, now it will become a function of h. So, it will become power series in h, right. a0 plus a1 into a. So, this is the constant plus a1 into h plus a2 into a square plus 2h, all these things. So, so coefficient of h has to be now, so it will change. So, how are you going to find it? You are really going to do all this expansion, do binomial expansion and then going to sum them up. Oh, it will be cruel absolutely. So, what would you do? So, Taylor said, okay, ultimately this would happen, it will become a, because a is fixed, it is going to become a function in h, a polynomial in h. So, it is c0 plus c1h plus c2h square plus cn hn. So, he said, okay, let us differentiate f with respect to h and let us see this what happens and calculate the c0, c1, all those things. So, f dash of a plus h, he wanted to calculate it at h equal to 0. So, if you calculate the derivative of this, so it will become c1 plus c2 c2h plus 3 c3h square plus so and so n cn h n minus 1. Now, I am doing it at h equal to 0. So, I am computing it at h equal to 0. So, f dash a at h equal to 0 means f dash a is equal to C1. What about C0? Oh, just put h equal to 0 here. If you put h equal to 0, fa is equal to C0. So, your C0 finally is fa. So, your C0 is equal to fa and f, and now how to find C2? So, we take the derivative again, f double dash a plus h at h tends to 0 as h at h equal to 0. So, see, all these derivatives are assumed to be not assumed, is continuous, because the polynomial will have a degree of derivative to up to infinite order, right. Up to nth order, anyway it will have, and then you can just going on, it will just go on, it will give you 0 derivative. So, it is always differentiable. So, all these functions are continuous, all the derivatives are continuous. Now, what is happening is that here, if I do the second derivative, means I take a derivative of this. So, it will become 2c2 plus 6c3 h square, so 6c3h plus n minus 1 cn h n minus 2. Now, you calculate this at h equal to 0. Once you do that, you will immediately see that f double dash a by 2, which we will, for some reason we will now write factorial 2, it is equal, or all this as 1 by factor, is equal to, this is equal to C2. Similarly, you can try out with the third derivative. So, what will happen? It will be 6c3 plus, I am not writing the other terms, n into n minus 1 into n minus 2 into Cn into h n minus 3, all evaluated at h equal to 0. So, what will be this? So, it will become, separating them. So, now I will have f triple dash a by 1 by 6, which is 1 by 3 factorial, that is why we have just taken this factorial writing, and that is beautiful, it will always come like that, is equal to C3 and so on. So, what is the general form of this C0 C1? So, in the general case, Cn, right, or not Cn, on any C nu, say, C nu is 1 by nu factorial f, the number of times is differentiable, f nu, I am not writing dash dash dash, f nu means the number of times it is differentiable at a. So, finally, that f of a plus h can be expressed as summation nu equal to 0 to n 1 by f nu a into h nu. And you can ask, what about when nu is 0? So, there is this standard convention in mathematics. I told you once that lot of mathematics depends on convention. 0 factorial is 1. So, this is what Taylor achieved. So, if you know the value at one point, right, then you simply know the value at any, if you know the value at a, then you simply know the value at any other point. So, and it is just a finite series, it is just finite, it is very simple. So, you just calculate the derivatives and you see. Now, it is always not easy to calculate the values of polynomials also, because it involves a lot of power. So, this will immediately do it. So, you just do not have to bother about the power, you have to just know what is the difference between the two values and take the power of that. Just take the power of a number and take the power of sum of two things, and express binomial thing is not always easy. So, the intuition that Newton gave to Taylor was the following, that if you do not have a polynomial function then what would be the situation? If you do not have a polynomial function, then suppose f is differentiable or and continuous up to n times, and or it is differentiable n plus 1 at time, whatever. So, intuition was this. The intuition is that if you know A, then f of A plus h can be approximated by a polynomial up to certain degree, and then there will be error. So, what you are trying to say is that given any continuous and differentiable function which has so many derivatives, say derivative up to nth order which is continuous, can be approximated as a polynomial. So, he says okay, because if a function is, as we have been telling when we were talking about Lagrange mean value theorem, that a function, if h is very small, it can be approximated by a linear function f a plus f dash a into h, the derivative. If it is better if you approximate it, it is a better approximation if you take a quadratic function where the second term comes. It is a much better approximation if you take the cubic term comes. So, if you increase, so those are the, so you get a nth order polynomial plus an error. So, basically what you are trying to do is, given a point where the derivatives can be calculated, you are trying to approximate the function value by using polynomials, because polynomials use those basic arithmetic operations. To compute a polynomial, you use basic arithmetic operations, multiplication, division. Even taking a power of an object, power of a number is also nothing but repeated multiplication. So, he said okay, you will have this. One factorial plus this part plus Rn plus a remainder term. So, this remainder term, this is an idea that we have to take from the last lecture, that a function which is not a polynomial, 1 by 1 minus x is not a polynomial, but that it could be approximated by the polynomial Sn plus Rn, a remainder term which vanishes as n goes to infinity. That is the key idea. So, that idea which Newton already had, because he had figured out the binomial expression, that idea he told to Taylor, that this is the idea you have to follow, that for polynomial term, when it is a polynomial, you do not have Rn, because n plus 1th order derivatives are 0. But if you have a function who has n plus 1th order derivative and rest of the up to nth order derivatives are continuous, then you can have a polynomial expression and the Rn term could be possibly written in terms of that n plus 1th derivative. So, this is the key idea that Taylor gave to Newton, and then Taylor figured that out. So, the first part, this part is called a Taylor's polynomial. This part is called the Taylor's polynomial, and this is the remainder term. Now, what is the remainder term? How does the remainder term look like? To prove how does the remainder term look like, it needs a lot of work to be done, which we are not going to get into, and because in the last class we do not want to get into too much details. So, Lagrange figured out that if there is the nth plus 1 derivative which need not be continuous, I can write the remainder term in terms of that is f of a plus h minus this part can be written in terms of the n plus 1th derivative. And how can it be written? So, Lagrange suggested that the remainder term can be written as follows, and this is quite suggestive. So, let us just look at the intuition of it. Theta is lying between 1 and 0. So, basically a plus theta h is a point between a and a plus h. Suppose assuming a is positive or negative, does not matter, it is some point between a and a plus h. So, a plus theta h is somewhere here. See, what is the intuition between such a writing of the remainder term? This is Lagrange's form of the remainder. This is called the Lagrange's form of the remainder. You can see derivations from the books and many other places, but I just want to give you the key idea. He says that, okay, suppose this was a n plus 1 degree polynomial, what would have happened? By what Taylor was writing, it would be nothing but 1 by n plus 1 factorial fn plus 1 a into hn plus 1. Look at the key idea here. If it was a polynomial, Rn would be, if it is n plus 1 degree polynomial f, Rn would be nothing but this with n plus 1. That would be Rn. It will be 1 by n plus 1 factorial f of n plus 1 a by h n plus 1, that would be Rn. But it is not a polynomial. But suppose in my mind I want to think that it is like a polynomial, then I would say that, okay, I am able to do an exact manipulation, an exact expression, but not with f nu of or f n plus 1 of a, but f n plus 1 of some form like this, a plus theta h. So, basically he was telling that I am somehow, so this is the nth order expression, right, Taylor polynomial Pn. So, Taylor's polynomial is this, right. So, he is telling that essentially because it is not a polynomial, I would have, instead of just a, I would have not just a but a shift from a. See, I cannot go beyond a plus h, I have to remain within that. So, I just, if I move away from a, I will capture that error. So, it cannot be fn a because it is not a polynomial, but it could be something a little bit different that will actually pull in the error and make an exact representation. So, I can have it as a plus theta h into hn minus into hn plus 1. So, that is the, sorry, here I should have also hn plus 1, sorry. So, this is the Lagrange form of the remainder, and this is what, do not forget the hn plus 1. So, this is the basic intuition. I am not going into the detailed math because detailed math would require detailed math and a detailed discussion, and that we have no time for it, and in many cases you have to use possibly the mean value theorem, integrals and all, which we have not taught. So, here let us just have the intuition. It is much better to have the intuition clear than anything else. So, what is the intuition? Once again, if it was a polynomial, I will have a, this is thing with just theta is 0. So, theta is something which is capturing the error. That is the key idea. Theta is something which is capturing the error here, and so he is telling that, okay, because it is not a polynomial, I might not have this, I might not have fn a, but I will have fn a plus theta h. So, yeah, if I calculate at fn a, it will not be an exact representation, but if I calculate it little bit off from fn a little bit off from a, then it might give me. So, there is some theta, for some theta, so I cannot pinpoint the theta, it depends on the choice of a and h and all those things. So, theta depends on the choice of a, choice of h and all those things. So, this is the key idea. Now, what would happen is that when is Rnx going to 0?
In general, for any function.
No, I am taking non-polynomial function. For polynomial function, theta is 0. Please understand. I am making sure, I am telling that this function is not a polynomial one. For it cannot be 1 also, right? Because 1, how can it be? You are trying to compute the value of a plus h. This is actually a higher level application of the Lagrange mean value theorem, so which we are not doing it. So what would happen now? How do I know that this sequence, is there any condition under which this remainder term would actually go to 0? Now assume all these A and A plus H, A and A plus H is contained in some bigger open set, say C and D. Okay. And in that open set, open interval, not open set, I am very sorry, open interval, all the functions are, all the derivatives are continuous and all those things. Now assume that f of n plus 1, this is also continuous function in that interval CD. And then what would happen is that in the closed interval A to A plus H, so if I take this and if I take the function fn Ax in the closed interval A to A plus H, then this is a bounded function because it is continuous. Then your Rn, mod of Rn, so this would be less than some m, this one becomes less than equal to mod of h n plus 1 mod of n plus 1 factorial into some m, which is the bound of this function. Now the question is that when can we show, so now as n tends to infinity, what happens to this? So there are several cases where we can show that n tends to infinity. Now if n tends to infinity, Rn goes to 0, then what we get is that fx can be expressed as a Taylor's power series, that is f of a plus h then becomes summation nu equal to 0 to infinity 1 by nu factorial f nu a h nu, right. So it becomes a convergence series provided Rn goes to 0 and n tends to infinity. It is not that every time Rn will go to 0, it will go for 0 for certain examples and what we should be looking at. So now if A is 0, suppose I put A is equal to 0, and suppose now then in that case you will have f of h is equal to summation nu equal to 0 to infinity 1 by nu factorial f nu 0 h nu. So this, when I have written in terms of 0, I have done the expansion in terms of 0, that is A is 0, and this is called the Maclaurin series. I have forgotten the spelling, Maclaurin series. Now the question is, in what case I will be able to, let us take an example where we can actually show that we are able to make Rn tend to 0 as n tends to infinity. Let us show the first one example, then we will say that we can express it in a power series. Having this does not say that it will go to 0, only we can say that mod Rn is bounded. So as n goes to 0, so what I am creating is that error is bounded above by some quantity, but that is depending on h, and n plus 1 factorial also blows up, but whether it goes faster than hn plus 1 to 0 or not, that we do not know. That depends on the specific example, specific situations basically. So only we have proved that Rn can be made to be a sequence bounded by a function of h. That is the only thing that we can show, provided this is there, otherwise we can't even show that. So let us take an example, a very important example, the exponential series e to the power x. I am rubbing all these things off. So if I take e to the power x, e to the power 0 is 1 plus x square by factorial 2 plus x cube by factorial 3 plus the last term x n by factorial n plus r n x plus r n. So, or r n x if you want to call it, because we are choosing that particular x. So, what is this r n? R n is nothing but, so what expansion we are doing here? So, we are doing an expansion of the Maclaurin type. This is your h. So, here f dash, so this is, you are taking the first derivative, second derivative e is nothing but e to the power x, and when you put 0 they are just 1. So, it is the Maclaurin type expansion. Let us see what is R n. R n is x to the power n plus 1, sorry, n plus 1 factorial e to the power, a is 0, 0 plus theta, h is actually h x now, theta x, where theta is between 0 and 1. So, let us look at this. Sorry, mod R n is equal to mod of x n plus 1 n plus 1 factorial to mod e to the power theta x. Okay. So, let us look at this quantity first. Let us see what is this. So, I can write here as x m by m plus and maybe x m by m factorial, x by m plus 1 factorial, sorry, m plus 1 into n plus 1. As up to m factorial, you write that with powers and then you separate them. Just a second. Now, you see we have broken up xn plus 1 by n plus 1 factorial into these things, you can understand, right. So, how many terms are here? Here we have n plus 1 minus m terms, right, m terms are being taken off. And let us now take m such that value of m is strictly bigger than 2 of x. So, we have fixed up an x and we are just looking for that particular x, and because our x chosen will be arbitrary. So, this game will operate for all x. So, whatever be the x, it does not matter, you always choose m, take a m such that m is strictly greater than 2x, that you can choose, and you can always choose your n to be bigger, much bigger than that m, because you know this is infinitely differentiable, this e to the power x. So, then for any k bigger than m, mod x by k would be strictly less than half. So, you just bring it like this, say m bigger than k, so mod x by k is less than half. So, basically it means this is less than half, this is less than half, up to this less than half. So, here this simply means this is x to the power m by m factorial, each of them is less than half, and I told you there are n plus 1 minus m quantities. So, there is 1 half into n plus 1 minus m to the power n plus 1 minus m. Now, this is less than, so this is a positive thing. So, 2 of x obviously is bigger than x. So, mod 2x to the power m is bigger than this, so it is less than this. So, what would happen once you write this 2 to the power m will cancel up with this one and will leave you just this. Right. So, now what is Rn? Rn is less than equal to this. Now, what is e to the power theta x? Theta x is less than mod of theta x, that is theta x, when any x is less than mod of x. So, because it is an increasing function e to the power theta x or non-decreasing, e to the power theta x is less than equal to e to the power theta mod x. And since mod theta is less than 1, so this is less than mod x. So, this is again less than e to the power mod x. So, you will get this one into 1 by 2n. Now, as n tends to infinity, this is a fixed number m, we have chosen some number m which is fixed. So, this part and x is fixed anyway, this is independent of n. So, as n tends to infinity, 1 by 2 to the power n goes to 0. So, from here we have proved that Rn goes to 0 as n goes to infinity. Now, this thing is done for every x. So, I have chosen one x and taken 1m and proved it for that. Whatever x you do, I will prove it. It is the same story. So, which means now e to the power x can be written as a power series, which you know very well. This is something you have possibly taken into your memory. There are several other important functions like sin x, cos hyperbolic x, which have this sort of series which are holding for all x. For example, 1 by 1 minus x, you saw it does not hold for all x. So, here it holds for all x, and that, so these are actually Taylor's representation. There is an important question which result which I have not stated, but I will ask my TS to put in the board, is that every function need not have a Maclaurin's expansion. There could be a function which has, you can compute the derivatives to any order at 0, but you would not be able to get the Maclaurin's expansion. But let me give that example and then end it. So, here I will give an example where even though you can compute the derivative at every point 0, because at every point, every level of derivative you can compute at 0. See what happens, just by computing at 1.0 need not give you the expansion. The idea says that the function has to be differentiable in a neighborhood, right, containing 0 and h. In a neighborhood containing 0 and h, the function f should be differentiable and all the derivatives have to be continuous up to n or n plus 1th order. Then only this is true. Now, I will give you a very important example. This is many times asked in interviews or any other thing. This is a very very standard example which I want to give. Where the Maclaurin series cannot be handled, that is you have the function that is n x is equal to 0. This has derivatives of all order actually at 0. So, f nu equal to, look at this function f x equal to e to the power minus 1 by x square, x is not equal to 0, equal to 0 and x is equal to 0. Looks very strange, but f nu 0 is equal to 0 for all nu 1, 2, does not matter, for any order of any value of nu f nu 0 is equal to 0, it exists. But take any h or any x, it is e to the power minus 1 by x square. So, that cannot be expressed through this expression, because f of 0 is also 0. So, this one side is just 0. If you do the Maclaurin's expansion, so Maclaurin's expansion is 0, but here for x non equal to 0, e to the power minus 1 by x square is not equal to 0. So, just by having the derivative at one point, the point 0 does not tell you that Maclaurin's expansion holds, because you have to have the derivative existing and continuous at all points in a neighborhood containing 0 and h, and that is what is not true here. So, Maclaurin's expansion always need not hold. So, this is some important example which is there, and with this I end the course and hope that you have liked it and hope that this would help you to investigate further. I will tell my TS to write down more series about sin x, cos hyperbolic x in the portal, and so that you can learn it. And thanks to everyone for giving a concentration, and hope this will be useful in whatever you do in the future, and all the best for all the students who are listening to this, best for them, and all those who are possibly elder have done something else already, have accomplished what they want in their life, but want to have a journey into the calculus, all the best for them also. There are so many texts, you can go and enjoy yourself. Thank you very much. Thank you once again.